my name is Luis. I'm part of the same research group as Guada and Josh, led by Kirill. And my presentation will be more focused on the data analysis, on the data visualization of all the results that Josh and Guada presented before, than the most deep, like machine learning aspects behind it. And my presentation will be like divided in these three topics: how to mathematically represent the ingredients and recipes first. This is a very important point to be able to make analysis that we want, not only in a COVID-19 perspective, but as well as cancer, diabetes, and obesity. I'm going to touch a bit these three topics, and not only mathematically representing those ingredients, but as well as the recipes made of the same ingredients. Then I'll go through a model that I developed that is able to retrieve the cuisine a specific recipe belongs to, for example, North American, South Asian, etc. And lately, for each one of the 4 diseases that I mentioned, obesity, diabetes, cancer, and COVID. And if you can see, one is like an infectious disease, COVID-19, obesity and diabetes. They are very much more related to lifestyle factors, as well as with an important genetic background on it. And then we also have cancer, where we are going to show to you that and for the others as well, that's not only about like the positive molecules that we can find in these foods, but as well as the negative ones. And this is the balance that we have to find. Although, and as it's stated in some articles, most of the times it's more about the positive compounds present in a given recipe than the negative ones. And although this can be a bit controversial, but in the perspective of the fast food lovers, can be good news. So regarding now how to mathematically represent ingredients and recipes, consequently, the first thing that we have to represent ingredients, the easiest way is to use vectors. And those vectors, usually the dimensionality of those vectors is proportional to the number of different ingredients in a given data set. And it's hard to work with vectors with many components. So that's why it's important to keep them small. And there are multiple techniques that we can use to represent ingredients into vectors. We have one that is called word2vec, that takes, in our case, recipes as lists of ingredients. And based on the context of those ingredients in the recipe, for example, ham usually appears often with cheese. In that case, it will attribute a vector to ham, and it will attribute a vector to cheese that are closer in the Euclidean space, and so on, so on, and so on. We have, and at the end of the day, we are going to have like vectors that are short in the number of dimensions, using, for example, this approach that I told you, word2vec, that allow us to transform them into vectors, and much easy to process them and use them with our machine learning tools. So although we have this side of these techniques, one example is the word2vec, where it receives, like in the case of recipes, a list of ingredients belonging to a specific recipe. And then for each ingredient, it can come up with a vector, and then the recipe will not be nothing else than the sum of all vectors, or more correctly, the average of the components for every single vector corresponding to the ingredients in the same recipe. Or we also have a different techniques that are called graph embeddings. And in the case of graph embeddings, the way that each ingredient is seen as a part of, as a node in a graph, and the connections between nodes they represent the probability of co-occurrence for these ingredients in the same recipes. And there's like two big approaches that we can use when we are representing these ingredients as nodes, which are node to vec and metapath to vec. And these two approaches have an important thing that separates them. When node to vec, we use it when we have like graphs with where all nodes are of the same type. So in this case, all nodes are ingredients, and the connections between nodes are the co-occurrence between those ingredients. Although if we want to consider in the same network different types of vectors, different types of nodes, for example, not only embedding these ingredients, or in other words, converting them into vectors, not only considering their co-occurrence among recipes in the same data set, but as well as the number of, let's say, flavor molecules that they share, we have to consider a different embedding. An embedding that's able to take as input a graph with different types of nodes. Nodes that in this case are not only ingredients, but as well as flavor molecules. And usually considering all these extra dimensions, not only ingredient co-occurrence, but as well as their chemical composition, it's a way to get more precise embeddings. Although when we have these embeddings, when we convert these ingredients into vectors, although these approaches give us many times lower dimensional vectors, they still have more dimensions than the ones that we can visualize. And here on this slide, you can clearly see 3D representation. I'm going to play it again. 3D representation, 3D embedding of multiple ingredients, of the ingredients present in recipe 1 million. And the way that you can look at the embedding on the left and the embedding on the right is as closer two ingredients are in the space, as more likely they will pair better together in the same recipe, because these embeddings are exclusively based in the co-occurrence of two ingredients in the same recipe. And from this, we can immediately take out some conclusions. Looking at the 2D embedding, the one that was calculated using a graph embeddings, not word2vec. And something that we can immediately tell is that for the nodes, for the circles that are closer together in space, as I mentioned at the beginning, this means that more often they appear in the same recipes. And if we look at these, the two different colors presenting the same picture, we can see orange nodes and we can see blue nodes. Orange nodes are the nodes which are believed to contain a certain number of molecules with COVID-19 beating properties. The ones that Guada presented, talked at the beginning, and Josh later on in his presentation. And the radius of each circle is proportional to the number of molecules with these COVID-19 beating properties in the same ingredient. So there are like two things that we can immediately take from here. One is if we don't have, like, for example, an ingredient available, and we have like multiple ones, we can just like go here to the image and see. For example, let's pick cauliflower, and it's cauliflower and broccoli are one of the top two ingredients that are believed to contain a higher number of these molecules with anti-COVID-19 with COVID-19 beating properties, because, as I said, like the radius is bigger. And if we want, for example, to make a recipe with these ingredients that are known to contain a very high number of those molecules, we can straight away come to the image and see, okay, so for example, puree or watermelon, it's quite an unexpected mix, but as the model says, it's more likely that they will pair together, watermelon and cauliflower, than, for example, cauliflower and mango, which is much further away. And to get to this point of to be able to represent these ingredients in the 3D space or in the 2D space, we need to use something else, a method that is able to reduce the dimensionality of the initial vectors that we obtain using the graph embeddings. And,
Luis, sorry, could I stop at this point? Because I just want to sum up what's happening on this graph. So on the right-hand side, we can see orange nodes. And if it's a large node, sorry, I'm looking at the right-hand image, not your left-hand embedding. If it's a large orange node, then that's a food with many of the antiviral properties.
yeah.
And then distance from another node, does that tell you something about the synergy between those two ingredients? So if you had cauliflower and watermelon, they're near each other, that gives you one kind of information, but cauliflower is very distant from another thing, so you wouldn't want to put those two foods together.
Exactly, because like this analysis is exclusively based in the co-occurrence of ingredients in the same recipes. What we can tell here is these two ingredients should pair good if they are like very close in the space, or it's not expected them to pair well together if they are further apart. Although if we account, as I said before, like not only when we have these graphs at the beginning where each node is a different ingredient, if we not only account for co-occurrence, but also if we account for specific molecules, in that case we'll be able to tell that not only two ingredients are believed to pair well together in the same recipe, as well as to share like some specific chemical molecules. And in this case, in this later case, we'll be able to infer that if a specific ingredient has like a given molecule, then the other one that's close in the space might have it as well, if we account for chemical information in the initial graph that we are considering it.
And so it's the chemical information that helps us to draw these graphs. So, you know, if we've got the distance between two nodes, is that because we have molecular information about that food that tells us that these two foods should be very distant in the graph?
Yes, that could happen if we're considering that chemical information here. But here is only if two ingredients appear often in the same recipes, they will be closer together. That's all in this case. Okay. And yeah, and the recipe and the data set that is behind this approach is one of the biggest ones with the available recipes, which is called Recipe 1 Million, with more than 1,000 ingredients. And because of its dimension, it can let us take some reasonable conclusions about like these different pairings. So right now I explained how to get from ingredients and recipes and to convert them into vectors. And it will be with these exact vectors that we did all the further analysis. But now the second part of my presentation was to show you how to extract the cuisine from a recipe. And here, when I say a recipe, I'm only considering it a list of ingredients, because to train these AI models, we need to have like two things. We need to have, in the case that we want to extract cuisine, we need to have like what are the ingredients in the recipe, and we need to have like a data set at the beginning that tells us this list of ingredients is associated to this cuisine. The other recipe, and consequently the list of ingredients, is associated to a different cuisine. So we need to have at beginning data that is able to tell the model this list of ingredients is associated to this cuisine. And with this, we manage to build a model that is able to predict with reasonable accuracy some of the cuisines that are shown on the table on the right. And I would highlight East Asian, Latin American, North American, and Southeast Asian, where on average 3 out of 4 um, recipes predicted as one of those cuisines are actually from one of those cuisines. And so that in case you are curious about it, this is how it looks like, this data set that I'm talking about. I know it's a lot of text, a lot of too many words, but in the first columns, you can see the identification of the cuisine. Here, you have like the African one, for example. And if I scroll down, you'll have all the others. And further on, you'll have like the list of ingredients that correspond to this cuisine. And the model was trained. And what is the purpose? What's like the advantage of knowing what's the cuisine a recipe belongs to? But before going to this part, I'll just explain what is the image on the left. And it's nothing else than, on average, most of the recipes have 10 different ingredients. This is just like a way to have a better understanding with what type of data set we are working on. But now why do we want to get to the cuisines? Just like when you are ordering food in Uber Eats, let's say, you have the option of picking, I want a Chinese restaurant or an Asian restaurant, I want Indian food. And if we have that option of picking the restaurants in terms of the cuisine, why not in the future have a food recommendation system built, asking for recipes as well based on the cuisine? So this more in the perspective of a nice to have like feature, but in the perspective of having something that is really, really useful, I can tell you that there are studies that associate cuisine to the predicted number of negative interactions of the recipes in those cuisines with the anti-neoplastic drugs, for example. So you have like, on average for North American cuisine, those recipes, those ingredients interact like 1% of the times bad with with drugs that are used to treat cancer. And this tells us, if we know what is the cuisine immediately that a recipe belongs, we can already have like a clue about how healthy that recipe can be. And another interesting approach will be for this recipe 1 million data set, the one that belongs the ingredients that I showed the embeddings before. We can see, and by processing each one of the recipes in this data set, which are recipes from around the world, we managed to extract the cuisines, so that each one of those recipes belong, and build them up where it was identified on average what are the cuisines with the highest number or the lowest number of molecules of recipes with ingredients, with molecules, with cancer beating or COVID-19 or any other beating properties. In this case, cancer beating properties. And one very a result that we got it from was exactly identifying that countries, Mediterranean countries, are countries where the cuisines, the South European, the Middle East, and the African cuisine, that on average have a higher number of ingredients with cancer-beating properties. And this can be a way as well to help us picking next traveling destination. Why not? And so keeping in this with the architecture that was used to get this exact model. It was an architecture that is called BERT. Computer vision had a is in a very fast-paced developing from the past. The main reason why computer vision was like so developed compared with all these machine learning algorithms in natural language processing, which is called this way when we are working with text, is because pre-trained models were made available much earlier. And when you have an AI pre-trained model, it means that someone else prepared that model for you. And in that case, you, with only some slight changes from that model, you can use it to almost a completely different task. It cannot be like completely different. But you can repurpose the model that someone developed with their data to your specific task. And one of the main reasons why natural language processing only started becoming the hotter issue lately was exactly when BERT was first released, which is a transformer, neural network architecture that enables us to take a meaning from text. And this text can be recipes. For example, a list of ingredients, we can see it as text and as a sentence. And from that sentence, what we want is to extract what is the cuisine that the list of ingredients belong. Or we can use these transformers for a different perspective, such as simply whether a specific message that we received in our email is spam or not. So this is a very a big approach that we can use it for. So keep going with this, and then you have like two other models that are from the same time, but at least a bit less, more recent, but more complicated to work on. So the first activity that I wanted to propose to you, and the activity number one, is based on the list of ingredients on the left. And I think we can do it here all together. The only thing that I'm going to ask you is to write in the chat box which cuisine do you believe that each one of the list of ingredients belongs to. For example, in that case, you type in the text box list of ingredients, just 1A, 2B, 3C, etc. Accordingly to what you think these list of ingredients, which cuisine they belong to. And the way that these machine learning models work is that they're able to find patterns in the data set that we've given before. If you remember, there's like many lines where at the beginning there's like the cuisine and then the list of ingredients on the side. And the way that these machine learning models work is that they are able to find patterns, like ingredients that are most often present in one cuisine and that they are not on the other. And yeah, so this is the challenge that I leave to you. And I can tell that this machine learning model that we train, this transformer, managed to predict correctly 3/4 of these cuisines, and I'm quite interested to see based on these list of ingredients if you are able to as well. But don't forget that this model predicted 3/4 of these cuisines correctly, but he predicted it, or it predicted it, in half a second. So this is already let's see if you can do better than that. And yeah, I'm probably going to stop sharing my screen. But I cannot stop sharing my screen, otherwise you'll not see the list of ingredients and the cuisines.
So, Luis, on this slide, in a way, it's already been answered, hasn't it? So we know that the algorithm could or couldn't predict in these cases. So what do you want us to do?
In the chat box, just to write list of ingredients 1, and then the letter on the side. List of ingredients 2, and then the letter on the side, whether you believe it belongs to cuisine North American, Latin American, Southeast Asian, or East Asian, for example.
I would do something like 1A.
Yeah, exactly.
That was my prediction. Okay.
Just to make it easier.
Okay, Neve's had a go. Let's all try.
I need like one of you to tell me what are like the guesses, because I cannot take away the slide from here. Otherwise it won't be visible anymore.
Okay.
But just have a look on the ingredients. there are like some clues on the list of ingredients. This is like not completely random.
We get some results coming in, so let's just wait for a few more suggestions.
Yeah, sure. And at the end of the day, this is not that bad. Like having like results around like 70% accuracy of prediction for the model, because we are working with like quite a lot of data, and at the end of the day, like small mistakes, they don't have like that a big impact, because that's the advantage of working with big data. It's more like the overall, like the general perspective that we are trying to retrieve, than going in detail on how many predictions were correctly or wrong. Though it's important to have like a minimum accuracy. Basically, these cuisines were the ones that performed better for the model, much related to the fact that the data input to the model, the one that was used to train the same model, had much more cuisines, recipes of those cuisines. So he knows better, or it knows better, what to expect from each one of those.
Well, we've had 12 suggestions, Luis, so I don't know if you need to close the slide to look at the chat. I don't know if you want to
yeah, and then I will, yeah, and I'll share again. So I'm really curious to see. So Jeffrey, one.
Neve was the first one, so if you scroll up, I think Neve at 12:48 was the first person to make a suggestion.
Let me see. Just put side by side here. Who was the first person?
12:48. Yeah.
12:48. Okay. So, okay. Probably before going forward, I'll just put in the chat what is like the correct answer, which is one belongs to, and then I'll share again the slides.
Okay.
So the first one is Latin American. First one is Latin American, and then the second one is North American. The third one, East Asian, and then I'll see, and then the last one is Southeast Asian. Okay, this is the correct answer. So 1B, 2A, 3D, 4C. Yeah, this is it. Let me see. Oh, someone had here like a. Let me see again. So we have 1B, 2A from Niam Homani, 1B, 2A, 3D, 4C. That was correct. That was impressive. We also, the guess from Carol is 50% correct. So sorry to tell you, but machine performed better in this case, Carol. And in the case of Stella, in the case of Stella, it was 25% accurate. K mock, it was 50% correct, 50% correct. But you can see, guys, that you still took some time. This model make it in like less than 1 second, and 70% accuracy is not that bad. But I'm still quite impressed with your answers, and there is still a few more, but generally there was very good answers.
I think there are 7 correct answers, but as you say, Luis, it's the speed. So it took me probably a minute to kind of assess those, whereas the machine can do that in a far shorter time.
Exactly. And now that you are seeing my screen again, we can tell like there's like some ingredients that it makes that let us like easily infer the type of cuisine. For example, like the presence in the case of Latin American, it's very common to have present like corn and cheese, like two ingredients that are very much like present in Latin American cuisine. In the case of the second one, like beef and essentially beef and potato, and are very much present in the North American one. In the case of the third one, sesame oil, soy sauce, they are common ingredients in the East Asian. And in the case of Thai pepper, it doesn't leave us like many doubts about the Southeast Asian prediction. And now that I'm getting like very close to the end of my presentation, I just wanted to make it clear that these tools that we are using, they can not only be used to find what are the ingredients that might contain the highest number of COVID-19 beating properties. This is an infectious disease, but there's also other diseases that by having like they are much more like lifestyle dependent, they can even have like even a short-term impact, an impact that can be seen like in a few days instead of a few weeks or instead of a few months. In the case of diabetes, for example, there's like two types of diabetes type 1 and diabetes type 2. Although diabetes type 1 is known for having like a very important genetic component, diabetes type 2 is like, it's very much related with how people eat during their lifetime, if they consume much sugar or not. And in terms of nutritional guidelines for people with diabetes, reducing the intake of sugar, it's like the most important one. For obesity, as you can predict, is like it's mostly related to avoiding the foods that have a high number of calories. And if you manage to provide recipes and food that contain a lower number of calories, the impact on this disease, which is a disease since very recently, considered a disease since very recently, and lately for cancer, it's known that nutrition has like a biggest impact for those cancers that are very tightly related to our digestive system. For example, mouth, esophagus, stomach, and but also many others. And it's not just like looking at like the positive effects of molecules like the ones that Josh and Guada present before, but as well as the negative ones. And these guidelines that I told to you, they can be easily found in many websites like from WHO, ECDC, CDC. And it's a problem when people look for these guidelines, especially when they are undertaking cancer treatments or treatments of any other diseases, and from unreliable sources, because at the end of the day, these nutrients might be stopping the treatment and making people feeling better, but in fact, they are not being treated. And my first activity, this will be very short. My first activity was mostly like recipe level. This one, I wanted to be more ingredient level, because as you saw, the topic of this my presentation was like ingredient recipe recommendation. So from these 4 ingredients, I just want you like to have a guess which one, based on what I said, do you believe can be like the best target for each one of the 4 diseases?
Can you describe them, Luis? Because is number 1 blueberries or black currants, and what's number 3? I can't tell what that is.
Tea.
Tea.
And number 2 is salmon, and number 4 is parsley.
Or celery, perhaps?
Or yeah, celery. Exactly, celery. Exactly. It doesn't make a big difference for these the disease that it is related to. And in this case, there is no competition with any model that it was previously developed. It's mostly like for you to stay in your mind what was like because before having like these paper published on the hyperfoods that are able to prevent and help treating, not preventing, but treating long-term symptoms of COVID-19, there's like a specific ingredient that is one of those that was identified with the highest number of molecules. There is another one of those 4 ingredients that was identified to have a biggest number of molecules with cancer-beating properties. And the other 2, I just hope that you can guess it right based on what I said on the previous slide. In fact, I should have mentioned that for people with diabetes, cardiovascular diseases, they are very often present. And in the case of leaves, they usually don't have a very high number of calories. So this is like the best news that I can give. And it's like mostly like to have the takeaway about like, yeah, I just wait like 1 minute or 2. And
Okay,
once we have a couple of answers.
Results are coming in. So far, most people seem to think that T is the anti-COVID molecule, though there are some other votes.
I mean, at the end of the day, like all these ingredients, they kind of enhance our immune system because of the properties that they have. So like very broadly, by enhancing our immune system, it's like it helps us preventing like already a big range of diseases. But I wanted to be a little bit more specific here. In the case of cancer and COVID, based on the predictions of the model of Quadra, and in the case of diabetes and obesity, based on the nutrition guidelines that are out there.
Well, so far from the votes we've got, most people think that food number 1 is the anti-cancer molecule.
And what about like diabetes and obesity? What are the guesses?
For diabetes, well, for obesity, which is 4, it's mostly celery. So mostly people think that obesity is celery because, as you said, there aren't very many calories. I think that's probably a good guess. For diabetes, which is C, it's a mixture of results, but I think most people have thought that it was salmon for diabetes.
Okay. So the answers are correct for diabetes and obesity. Diabetes very much because these fatty fishes with their oils rich in omega-3, they help us like preventing and avoiding those cardiovascular problems, which are very often like a problem associated to diabetes. On the case of the celery, nothing else than like being leaves in general, not only celery but also parsley and all the other and many of the others are low in calories, and still they contain a very high number of like important molecules that allow us to achieve our daily intake values, because there's like some standards that tell us as a day on average a person should get like specific number of grams of salt, specific numbers of vitamins A, B, C, D, and the same for proteins, sugars, etc. The only guess that it was not right was between cancer and COVID-19. It was the other way around. It was predicted as black currant to have like the highest number of molecules with the COVID-19 beating properties, and T in the case of the cancer beating properties. But at the end of the day, what I wanted to make it clear is imagine that you have like someone that has like COVID-19 and it's obese at the same time. There's like trade-offs that sometimes have to be found, and it's not a problem of finding what's like the best recipe, but optimizing what's the best recipe, because sometimes people might have more than one disease that for one you might need to have some more of a specific molecule and ingredient, but for the same other disease that the same person has it might tells you to do slightly the opposite. So this is why it's important to have like personalized diets and to be targeted individually. And this is the presentation I had prepared for you guys. Hope you enjoyed. And any other question? don't know if you still have time to go to the Slido. I had the one question there prepared for you, but once Josh didn't go, I don't know. I can just probably like ask like verbally if
Okay.
it's better.
Yep, we're here. Let's do it verbally.
And we can make it just So my question was, are all diseases targetable with nutrition? It doesn't mean that I'm not asking if you can cure all diseases or prevent all diseases. What I'm asking is that until some extent, can we expect to prevent or treat all diseases?
Oh. I think people who think you can, if you think you can treat all these diseases, raise your hand, and that would probably be the easiest way to see the vote. So if you believe you can treat all diseases with foods, raise your hand in using the raise hand function.
Imagine that you have all the tools, the computational tools to study them properly and finding like the molecules, just like it was done, for example, for COVID and cancer before. Like you have the data sets, all the information that you need to train like the best models.
So we've got some votes. We've got some votes saying yes.
It's increasing. And regarding this aspect, I gave like a small clue on the slide that I talk about diabetes, and on the slide that I said that diabetes has like a lifestyle component, but as well as a genetic component in the case of diabetes type 1. So I imagine that the ones that didn't put their hands up are the ones that don't believe that we can. And in fact, like the genetic ones are a small percentage. They are like the ones that are related to lifestyle factors are much more, but the ones that are related to genetics and how our DNA, how our genes work, it's very hard to change that using nutrition.
I think that's why we didn't have very many hands raised. So I think a lot of us think, you know, there'll be some things you can't alter the course of them by changing your lifestyle. So I think there's a certain amount of caution among our students believing that, you know, you can target all diseases using foods. I think I agree. I think I shared that caution.
Yeah. But the good news is that at the beginning it was like believed that cancer is like mostly genetically determined. And year after year, we are like discovering new lifestyle factor that has an importance in its development or not. So based on like the proportion of ones that are related to lifestyle factors and that are not, I think we have a lot to do. We have a lot to do, and we can not only improve like the number of years that we live, but as well as the quality of those years only using nutrition.